Welcome back to our discussion on combined gas vapor power cycles. What we want to do today is to basically discuss this concept of combined gas vapor power cycles, which is one of the last concepts to increase the efficiency of power cycles. And so let us begin that by talking essentially about gas power cycles. So we have been talking about gas vapor power cycles for quite a bit. And what we understand is that the turbine inlet temperatures for gas turbines are much higher than the average turbine inlet temperatures for steam turbines. Essentially, when we talk about gas turbines, the turbine inlet temperatures have reached as high as about 1400 degrees Celsius as compared to steam turbines, where the turbine inlet temperatures are around 600 to 650 degrees Celsius. So you can see this is a very big change. And because of this very huge difference, because of very high temperatures for gas turbine cycles, their efficiencies are relatively higher as compared to steam turbines. And this essentially comes from the basic Carnot efficiency formula, which says efficiency is 1 minus Tc by Th. Now, as we have discussed in the class, we don't follow this formula specifically when we are dealing with Brayton cycle or Rankine cycle. This formula simply provides us the direction. And as long as you go to very high TH values, you're going to increase the efficiency for the same value of TC. Now, the good thing about gas turbine is that we have been able to increase TH quite a lot. I mean, 1400 degrees Celsius is a very high temperature. And this has essentially increased the efficiency of gas turbine cycles over the past 20-30 years. Now, the problem with gas turbine cycles, especially in their when they're operated on their own without any other combination, is the fact that the temperature at which the hot gases come out from the steam turbine, the gas turbine is still very high. We're talking about gas turbine exhaust temperatures being around 500, 600 degrees Celsius. And this means that TC is, still on the higher side. For us to achieve higher temperature, higher efficiencies, we got to bring down this TC. And one of the smartest ways of bringing down the TC is basically by combining a gas power cycle with a vapor power cycle. Okay, and let's see how that all works together. So this is a schematic showing you a gas vapor power cycle, a combined gas vapor power cycle. Let's look at how this things work. So you have the air entering the compressor of a Brayton cycle or a gas vapor power cycle. Usual conditions 300 Kelvin, 1 atmospheric pressure. It gets compressed, comes out at higher temperature and higher pressure. Then it goes through this combustion chamber where a lot of heat is added essentially from an external source, the way we model it. And basically we have hot gases at temperatures approaching 1425 degrees Celsius going and expanding within the turbine. So this is a very high temperature, and because of and this essentially forms as the upper limit, or this forms the average temperature of heat addition, right? So now the gases expand and come out at state 8. Now at state 8, the gases are still hot. So instead of rejecting them into the atmosphere and wasting all that thermal energy available in the hot exhaust gases, what we do is that we send them through a heat exchanger. Now, this heat exchanger is called a heat recovery steam generator. And the reason it is called a heat recovery steam generator is because it does exactly that, in the sense that it recovers the heat from the exhaust gases, hot exhaust gases coming out from a gas turbine, and it transfers that heat to the liquid water that's coming in at a high pressure, and it converts that liquid water into steam. So essentially, it recovers heat from the hot exhaust gases from the gas turbine and uses that to produce steam or generate steam. And that's essentially happening through the heat transfer from the hot gases to the cold water. And so once you generate steam, then you operate the usual Rankine cycle. So the hot steam at already high pressure because it's being pumped. So high pressure, high temperature steam, 620, 630, whatever degrees Celsius, it enters the turbine, produces some work output for us. So we have two turbines producing work output. One is the gas turbine and the other one is the steam turbine. And here then we send this uh, steam, which is at, essentially a saturated mixture at much lower pressure and temperature or much lower enthalpy. We send it through the condenser where we reject it and convert it into saturated liquid. So this is essentially uh, how this entire process works. All right. So uh, the key point here is that what we are doing is very simple. What we are doing is we are mainly adding heat at a very high temperature let's say around 14, 25 degrees Celsius, and we are rejecting heat at a very low temperature, or mainly rejecting heat at a very low temperature, which is in the condenser. Now here, the temperature of heat rejection could be as low as 50 degrees Celsius. So instead of rejecting heat at 500 degrees Celsius, we are rejecting heat at 50 degrees Celsius. So again, when you go back to Carnot efficiency, 1 minus Tc by Th, Th was already very high because the only place where we are adding heat is in the combustion chamber right here. And this is happening at very high temperatures. Now, we had very high Tc before if you operate only gas turbine, but by bringing down Tc, by combining it with the steam turbine cycle or the Rankine cycle, we have been able to increase the overall efficiency drastically. And when we talk about efficiencies of combined cycle, efficiencies as high as 50%, 55% are the norm. There are combined gas vapor power cycles achieving efficiency of 65 to 67% already available on the market. In fact, you will have one such example to look at in terms of a GE combined vapor power cycle. So this is an excellent technology. And in terms of efficiency, it has given absolutely huge increases in the efficiency possible. Now, this is how the TS diagram would look like. We have two different working fluids. In the gas cycle, we have the main working fluid being air. In the steam cycle, it's of course steam or water. And the heat transfer essentially happens from this state 8, which is of course at a higher temperature than state 3, right? It rejects heat, it cools down, comes out at 9, and it basically helps this water, which was at state 2, a higher pressure but very low temperature. It allows us to get heated in a constant pressure process and get converted to steam. And so in terms of heat rejection, of course, the main part where we are rejecting heat is from 4 to 1, but also a tiny amount of heat gets rejected from 9 to 5. So this is essentially how this combined gas vapor power cycle works, and it's one of the most efficient power cycles on Earth. Okay, so this is about the combined gas vapor power cycle.